We're going to look at basically 3 topics today that are really all just different names for the same basic idea. And so we're going to kind of lump it all together. We're going to examine something called the power function, and we're going to examine joint and combined variation. Now your book gives these things separate sections, but they're really the same basic idea. We need to do 3 things. First of all, you're going to solve variation problems that involve the power function. We'll see what that is. We're going to solve joint variation problems, and we're going to solve combined variation problems. You will not need to be able to distinguish between them. They're all handled exactly the same way, so the names are really just a matter of semantics, and the principle is the same. First of all, the power function. If you have a variable that's related to another one, or some power of another one, we say that we have a power function. We might say that y varies with some power of x. Now, yesterday we handled the case where y varies directly with x. It's the same idea, except it might be some power of x. And there's a couple of very short examples that we can see that kind of demonstrate this idea. The key to all of these is not all the different forms of equations that we can have. Y equals k, x to the nth, y equals k over x, y equals k times x. You don't need to distinguish those. The relationship for the variation will always be told to you, and it doesn't matter what category it falls in. Let's look at a simple case. Z varies directly with the cube of b. With all these problems, the first thing you want to do is read that statement, because that is the key to the whole problem. That tells you what variables you've got and how they're related. So z varies directly means z equals directly, which means we're going to have k times, just like yesterday, but now instead of just b, we've got b cubed. And that's it. Now we do the same thing we did yesterday. It says that when b equals 7.2, z equals 268. So we take the case we know and plug that in to find k. So z equals 268. That equals k times b, which in this case is 7.20 cubed. Solve that. And we're going to have our k value that ties z and b together. 268 divided by 7.20 turns out to have a k value of 0.71802. And again, we'll leave plenty of extra significant digits on k, and we'll round it off when we're done. Okay, you don't necessarily have to do the math here, but do you see how we got k? So k equals, if you were to just do the algebra up here, k equals z over b cubed, and there's z and there's b cubed. So we get 0.71802. Then we've got our equation that relates z and b. We can say that z equals k, which we know to be 0.71802 times b cubed. There's the equation that relates z and b. So we want to find a z when b equals 3.65. All you got to do, plug it in for b, and you're done. So z equals 0.71802 times 3.65 cubed. And if you crank that out, you're going to find out that z equals 34.9. And we're done. Now, it was a direct relationship. Even though they're not going to go up by the same proportional amount anymore, it's still, we know that it's a direct relationship. So if Z, what did Z do? B went down from 7.20 to 3.65. What should Z do? Z should also go down, and it went down from 268 down to 34.9. Had Z varied inversely as the cube of B, then we'd be back to having one going up, the other one going down. And we're done. All right, the next one is an application from physics. Many of you have to go on and take physics, and you see that there's a lot of variation problems in physics because physical phenomena are always related to each other, and they can usually be described in this way. Here's one example. The frequency that a pendulum swings, I happen to have a couple of pendulums here. And the frequency at which this thing oscillates will depend on how long it is. Will that longer pendulum oscillate faster or slower than this one? It'll oscillate slower. Okay? So if we have the same two materials and the pendulums are otherwise the same except for their length, the two will oscillate at different speeds. And every pendulum has its own natural frequency. You can't speed up a pendulum. If I wanted to give this thing a push and somehow make it swing faster, it's not going to work. Every pendulum has one speed at which it'll swing naturally. Well, here's the fact, or a relationship. The frequency at which a pendulum swings is inversely proportional to the square root of its length. So let's write that relationship. The frequency, that's how many oscillations per second. How many swings per second is inversely proportional to the square root of its length. So what's your relationship? We can say that the frequency F equals inversely proportional tells you what? K over, exactly, K over. Directly proportional says K times, inversely proportional means K over. Inversely proportional to the square root of its length. So there's our relationship. Now, since they're inversely proportional, that means that the longer the pendulum, the lower the frequency, or the fewer number of swings it'll make in each second or in each minute. So there's our relationship. Here's the scenario, and this is actually suits this particular pendulum. This one is 46 inches long. Drew? Well, here's what we got. This one's 46 inches long, and it will cycle. I can tell you that last night I was standing in my kitchen with the microwave timer because it's the only timer in the house that measures seconds, and I was figuring out what the frequency is to make sure that this whole thing works. What we're going to do is we're just going to see how many cycles this thing makes in 10 seconds. Okay? So I'll watch the clock, and I'll tell you when to start. We'll start it, and I want you to count how many complete cycles this pendulum makes in 10 seconds. I'll watch the clock. You just count them. So one complete cycle is from up here where I release it back to here. All right? The other interesting thing is that the oscillation, the period that it takes to go back and forth, it doesn't matter how high you drop it from. If you drop it from up high, it'll get back and forth more quickly. But if you drop it from down low, it still takes the same amount of time to get back. An interesting property of pendulums. That's why when you've got a pendulum clock, you can get that pendulum swinging by bringing it back however far you want, and it'll always keep time. Okay, so I'll let you know when to start here, and then I want you to count the number of oscillations it makes right now. Stop. About 5.5. Okay. We'll call it 6. Because if it makes 6 oscillations in 10 seconds, then how many oscillations per second have you got? 0.6 oscillations per 10 seconds means you've got 0.6 oscillations per second, all right? In 1 second, it doesn't quit all the way back. It gets all the way down a little bit past halfway. No, here's our structure that we're going to have. We know that our frequency for the long one is going to be 0.6 oscillations per second. So let's fill in what we know and find K. 0.6 is our original frequency, and that equals K divided by the square root of, what's the length for this one? 46 inches. So go ahead and solve for K. K equals 0.6 times the square root of 46. It's 4 point something here, isn't it? 4.069, we'll call it, leaving plenty of sig digs. So that's a property of that pendulum, or of this material, I should say. 4.069 is our K value. So now we want to know how long the pendulum should be so that it will cycle at 1 cycle per second. So we go back here. We want our new frequency to be what? 1. So let's figure out what the value of L is that will give us that. So we know that our new frequency of 1.0 is going to equal K, 4.069 divided by the square root of L, and we need to solve that for L. Does that look okay? Taking our relationship between frequency and length, filling in the frequency we want, that's our K value that we just found, and now we'll find the length that we want. So solve this. Multiply both sides by L, and we get the square root of L equals 4.069. So L equals what? 16.6. So you should get a length of 16.6. That's the pendulum length that should cycle 1 time per second. So let's check it out. I happen to have a pendulum that is about 16.5 inches from its pivot point. Again, how many cycles ought to this thing make in 10 seconds? Better make 10 of them. So we'll start right now. Stop. How many was there? 10. It worked out. Okay. So now you can go home and build a clock this weekend. And we're done. I should have labeled this new L value our new length, minor point. But 16.6 inches is the length that will do that. Suppose Californians claim that their grapefruits have 25% more volume than those grown in Florida. How will their radii relate? If the California grapefruits are 25% bigger than the Florida grapefruits, how do their radii relate? Well, obviously the California grapefruits have to have a bigger radius. The question is the radius 25% bigger? No. So here's what we know. First of all, write your relationship. We already just established a minute ago that the relationship between volume and radius is volume equals K times what? R cubed. We already established that. So then we can say a couple of things. We can say that the volume of a California grapefruit is equal to K times the radius of a California grapefruit cubed, and the volume of a Florida grapefruit equals K times the radius of a Florida grapefruit cubed. Now, how are these two volumes related if the one from California is 25% bigger than this one? What can we say? The volume of the one from California equals what compared to the volume of the one from Florida? It's what? 1.25. The 1 represents that it's that big, plus the 0.25 represents 25% bigger. Okay, so it's 125% of the volume of the one from Florida, 1.25. Okay, those are the facts that we need to really get going here. That fact, and that fact. Questions about where those three things come from? Okay, so now what we really want to do is, the question is, how do the radii compare? So we need to find out a relationship like this one, but we need to do it for radii. Here's what we're going to do. We can replace VC with this value. So we're going to take this equation right here and say that instead of the volume of the one from California, we say that that's 1.25 times the volume of the one from Florida. And that equals K times RC cubed. In other words, we want to replace the V's with R's. And then we replace VF. VF is equal to so we took out VF and put in that. We took out VC and put in this. Now our equation involves the radii and not the volumes anymore. Okay, stop there for a minute. We took the volumes out, we put in the radii, because that's what we want to find how they're related. Now what happens to your K's? They cancel off. So we get 1.25 of the radius from the one from Florida cubed equals the radius of the one from California. Well, we want to solve what is the size of the one from California. That was the original question. So the last step here is to take both sides. How do you get our California by itself? Cube root of both sides. So we get so the radius of the one from California is, we just need to know the cube root of 1.25. Cube root of 1.25 is and the cube root of the radius of the one from Florida cubed is just the radius of the one from Florida. So it is apparently about 8% bigger in radius. An 8% increase in radius results in a 25% increase in volume. Joint variation. Joint variation is what you've got when it varies directly with two others instead of just one. For example, the area of one of these windows doesn't depend on just its width. It depends on what two factors? The width and the length. Okay, so it depends on two things, not just one. That's a joint variation situation. An example of this, again, you don't need to know all the different forms, but it's the general pattern. If y varies jointly with x and w, that just means that y depends on two things now, k times x and w. Then we can write that relationship. What things does the weight of this book depend on? Assuming that every book is made out of the same paper, what three things does the weight of this book depend on? The size of it. And what are the three things that make up its size? The width, the length, and the height or thickness of it. All right? So you would say that the weight of this book varies directly with the thickness, the width, and the length of it. Doubling any one of those, if we made the book twice as thick, it's going to say that it's twice as heavy. If we make it twice as thick and twice as wide, then it's going to increase by a factor of 4. If we made it twice as thick, twice as wide, and twice as tall, it would increase by a factor of 8. 2 times 2 times 2. What we can say is the weight of a book varies jointly with its length, its width, and its thickness. All three of those things will affect the weight. So before you start plugging in numbers, just establish your relationship. We would say that the weight, W, varies directly equals K times what? What's the rest of the relationship? Length, width, and thickness. What's that? Say that one more time. And the width. But we better use something other than W for width. Okay? So, that's okay. Yep. So it varies with three things. Jointly can be any number of other things, as long as there's no special powers thrown in, but it wouldn't really matter if it is. We would just give it a different name. So it's going to depend on length, width, which how about if we call that I, the second letter? We don't want to use W again, and thickness. I is width, so we don't use W again. Okay, well, there's our relationship. Now we just do the same thing we did before. Suppose a book that is 10 by 8.5 by 1.5 has a weight of 2.7. So weight is 2.7 when we have K times a width of, a length of 10 inches, a width of 8.5 inches, and a thickness of 1.5 inches. Okay, well, we've got those plugged in. Now we can find K. I should have put units on 2.7 here. Make a note that that's 2.7 pounds. Then we can solve that for K, and we get I left the units on here because the value of K has some meaning if you leave the units on. For example, let's take 2.7 pounds. Now we're going to divide these out. If you multiply these together, you get, 127.5 inches cubed. And that's equal to K. Now if you divide that, you get a K value of, keep setting my notes down here, 0.212. And what are your units on K? Pounds per inch cubed. So here, I mean, usually you can think of K as a meaningless number, but K does always have meaning. What does K represent in this scenario? It's in pounds per cubic inch, so that's telling you what about this book? It's not the volume, it's the density per cubic inch of paper. Okay, it's saying basically that these materials weigh 0.0212 pounds per cubic inch. We figured out the density of the material. Now, we don't need to know that to answer the question, but K value usually does have some physical meaning, even though we kind of breeze right past it. Now, what was our question? The question was find the weight of a book that is 9 by 6 by 3/4. Well, we just go back to our original relationship. The weight of the new book is going to be K, which we now know, times, we do assume, Amy, your comment before about the units, we do always assume that the units given in the beginning match the units later on. if you were to switch units, if I were to tell you this information and then say a new book is 10 centimeters by 30 centimeters, then we'd have a problem. But we won't consider that. You'd have to do some converting. I promise I won't throw that at you. No. Probably not. By 3/4 of an inch. Well, what happens to your units of cubic inches here? And you're left with pounds. So the weight in the new book is whoops, I missed a 0 here. Doggone thing. 0.0212 pounds per cubic inch. Make sure you make that note. And you should get 0.86 pounds. So a smaller book would weigh a little under a pound, assuming it's made out of the same paper. And we're done. Let's take this room. The area of this room depends on how wide it is and how long it is. I think everybody will agree with that. Let's say we make this room 30% wider but shorten it by 5%. We want to know what the net change on the area would be. If we make it 30% wider but 5% shorter, is the area of the room going to go up or down, and by how much? Start with your relationship. First sentence, area of a room varies jointly with width and length. Wham, right there. What are you told? Varies jointly with length and width. There you go. Okay, so you got your relationship established. Okay, so now we're going to do like we did before. We're going to have an original and we're going to have the new one. We don't have solid numbers to work with here. We've got percent changes. So we know that the area of the original room is equal to k times its original length times its original width. We'll call those subscripts of 1s, A1, K, L1, and W1. The new room has got to have the same fact. The new room, A2, equals K times L2 plus W2. We're just saying that the old room and the new room have got the same variation fact. Okay? Now, we've got some changes here. If the width is increased by 30%, what does that tell you? It's going to be 130% of what it was, or in other words, the new one, which is, I forgot, is this width or like the width? The new width is what? (130% of the original one. The original width plus 30%. That's our new one. So our new width is 30% larger than the old one. What about the length? The new length is what? Good, 0.95, 5% less. It's only 95% of what the original length was. Okay? Now we make those substitutions. We want to, again, what two things do we want to compare? What was the question asking? The things that we want to compare are, like the grapefruit before, it said, how did the radius compare? Now we're asked, how do the areas compare? So we want to say that we know what W2 and L2 are, so we're going to take this one and make those substitutions. We can say that our new area will be K times, not L2 anymore. Instead, we want to call it 0.95 L1. We're again putting the new one in terms of what the old one was. The new area is 0.95, the length of the original, and the width is 130% of the original. Okay, so we made those substitutions. Now what we really want is KL1, W1. That's the area. So we can let all those KL1 and W1 float to the back, which means we're going to take these factors and multiply them together and put them out front. So A2 equals 0.95 times 1.3. Take those constants and mix them together. 1.235 times KL1 W1. But we know what KL1W1 is. KL1W1 was really just the fancy name for the original area. So what we just found was that the new area is equal to 1.235 times the original area, which means you can answer the question, by what percent will, or what is the overall change in the area? Did it go up or down? It went up by 23.5%. It's got all the original area plus 23.5%. So the area increases by 23.5%. We had all the original area plus 23.5%. And we're done. Well, that leaves us with just basically one more case. Combined variation. Combined variation is everything else. Okay? Here's an example. If y varies with x, the square root of w, and inversely with the cube of z, you've got a combined variation. Again, that relationship has to be given to you. You don't have to figure that out. It's always told you. You just need to read what the words say. The one I have up there is not towards any specific problem. It's just an example how k can vary with three different things in any different way. Now, the only difference between this and joint variation is that in joint variation, they were always just products, L times W, or length times width times thickness. Whereas here, we allow any powers to be mixed in. It's when we combine the power function and joint, and we get all these different scenarios. So let's just look at an example. Here it is. N varies directly. So you write this down as you read it. N varies directly means you're right. N equals K directly with U, which means it's going to be K times U and the square root of V. So it varies directly with U and the square root of V. Does it square V? And the oh, I'm sorry, yes, square of V. So K varies directly with U and the square of V, but inversely with the cube root of W. There's your relationship. K varies directly, or in other words, you multiply it by U and V squared, but divide by the cube root of W. Okay, well, we have to be given one case for which we know all of them so that we can determine what our K value is. We're told that if N equals 72.5, when U is 5.83, and V is 8.62, and W is 27, so we have the cube root of 27. And we want to find out what... Thank you. Yes. That would have been disastrous. Yes, V needs to be squared. Okay, so now we can find our k value. So just seeing the algebra here, we're going to multiply both sides by the cube root of 27, which is incidentally 3. And then we're going to divide by 5.83 and 8.62 squared. So if we write that out just to see where that's coming from, we're going to have 72.5 times the cube root of 27 divided by 5.83 times 8.62 squared. K will turn out to be 0.5021. Now we know how they're all tied together. Okay, we want to find V when, so V is going to be the one that we don't know. When n equals 45.7, scoot that over just a little bit or I'm going to run out of space. U equals 8.25 times V squared over the cube root, cube root of 64. Solve for V squared. Okay? Okay, let's get the numbers shifted around so we can solve for V squared. I need to get some room here. So V squared is 45.7 times cube root of 64 divided by 0.5021 divided by 8.25. Once you get this result, you're going to take the square root and V turns out to be, did anybody crunch that out? 6.64. We got it. Well, let's do one last problem involving something like this, but with percents, where we need to work it out, and then we'll call it good. Here's what we've got. The volume of a soup can, this is actual data from a Campbell's cream of celery soup can here, is a 10 3/4 ounce can. We want to take this can and we want to make it 30% taller and make the diameter 40% larger, and we want to know what the volume of the new can will be. You don't know what the dimensions of this can are. I know you're dying to know, but we don't need to know. So our relationship is told us, we are told that the volume of a soup can varies directly with the height and the square of the diameter. So we know that. V equals K H D squared, directly with the height and the square of the diameter. Let's take our original soup can. V1, the original, equals K times H1 times D1, the original height and the original diameter. The new one is going to be K times the new height times the new diameter squared. Now, how does the new height compare with the old one? .30 times the original. And the new diameter? 1.40 times the original. told what the relationship is and how those two change, height and the diameter change. Okay, well now we can take our new one, which is what we want to know about, see how it compares to the old one, but we're going to substitute these values in for H2 and D2. So we have the fact that our new volume is equal to K times H2, which is 1.30 H1, times D2 squared, which is 1.40 D1 squared. Okay. Well, now what do you need to do? Do what? You got to take all those constants and pull them out of there. Okay, so we're going to have 1.4 squared times 1.3. Get all those constants out to the front. We end up with V2. 1.3 times 1.4 squared turns out to be 2.548. Times K times H1 times D1 squared. H1 and D1 squared float to the back because we have a name for K, H1, D1 squared. .548 times what is K, H, D1 squared? That's just our original volume. So this isn't what the question asked, but it's worth noting. By what percentage does the volume increase because of these two changes? Well, it's 254.8% of what it was, so it went up 154.8%. But that's not what the question is asking. The question says, what is the volume of the new can? What was V1? V1 was 10.75 ounces. So V2 is equal to 2.548 times 10.75 ounces. It's 254.8% of what the original volume was, and the new can's volume (27.4 ounces). New can will hold 27.4 ounces.